Let us recollect what we learnt in the last class. In the last class we learnt the basics of operation of a timer counter. A timer counter, as the name indicates, as a counter, and because this timer counter has to interface with a human being, the counter will always be a BCD counter with n and a half digits. The half a digit comes from the last carry of the BCD counter. We take care of that carry, we get double the count possible with n digits. If n digits, I get 9999, taking the most significant digits carry into account, we can get 19999, depends upon the number of digits. Normally when we talk about a timer counter, the n would be 10 or 12, right. Very rarely you will get 8 and a half digit counters. The counter value is latched and then displayed. Today this display would be mostly 7 segment display, either the segments of made of LED or liquid crystal display or LCD, right. LED, all of you are aware, is a diode. When you send a current through the diode, it glows, right. So each segment would be made of one LED if the segment is small. If the segment is large, you want really a large number to be displayed, then it may be made of 2 or 3 LEDs, right. You need to provide certain amount of current to make the LED glow, but it is quite bright and you can see in even white light. But that comes up with a price, which means you will have to expend some amount of power, right. Most of the timer counters are benchtop instruments, which means they are quite large and you have to keep it on a bench and connecting to a 230 volts or 110 volts power supply, as the case may be, will not be a problem. But there are some portable timer counters available, and when you make anything portable, you need the instrument to work on battery. When we talk about battery, the LEDs then really take a large amount of power, and the amount of working time for a given battery size drastically reduces when we have LED. On the other hand, the liquid crystal displays take almost negligible current, nearly zero current, so they help the battery energy stored in the battery go a long way in making the whole instrument work. So if you have a portable timer counter, the display would be LCD. In an LCD display, each segment is made into a small reservoir. So in the reservoir we have a colloidal solution which contains a liquid part and a solid part. That is why it is known as liquid crystal display, right. And the property of the liquid crystal is that when we send a small current I, the polarization of the light that goes through changes, right. Depending upon the type of liquid crystal that you use, it could be 15 degrees, 30 degrees or 40 degrees, whatever it is, right. So initially you put a polarizer and then send a normal light. The moment I put a polarizer here, I will get a polarized light, and I put a reflector. Without a current, I will get the same polarized light reflection, so I will see a reflector without any problem, right. The moment I send a small current through the LCD segment, the polarization that comes here is no longer P, but P plus theta, because the segment displays moves the polarization angle by an angle theta, right. And then when I get it back here, it is no longer P, I am going to get P plus 2 theta here, and what I will get is almost 0 light or drastically reduced amount of light. So when we send the current through the LCD segment, the segment appears black, right. That is how the whole LCD started, by suitably arranging not a white background but a colored background. It is possible to make color LEDs as well, LCDs as well, right. But most of the displays in Kramer counters would be monochrome, right, or mostly black and white LCDs, right. Because the current required to make the polarization turnaround is very small, in terms of less than a microampere, right. So the actual power taken by the LCD displays are quite small, okay. And then we have a local oscillator, which is a crystal piezoelectric crystal based oscillator, right. Here again most of the timer counters will have 100 megahertz as the base oscillator, and we have the digital circuits that process the input. Then we have mainly a comparator, so that we can give analog signals. And we also learnt that the timer counter can operate in several modes. The mode, frequency mode, the counter displays, the count is equal to Ts by Tx, where Ts is a set standard time period, Tx is the period of the unknown waveform. So we have 1 by Tx, which is Fx, so we get Ts into Fx. If I make Ts as 1 second, then I measure Fx directly in terms of hertz. If I make Ts as 1 millisecond, I measure the count tells me the unknown frequency Fx in terms of kilohertz. If I make Ts as 1 microsecond, the count gives me a count value which tells me the frequency of Fx in terms of megahertz, right. The second mode is the time period mode, that is why it is known as a counter timer. It can also function as a timer. Time period mode, the internal circuitry is so arranged that the final count value displayed is equal to Tx by Ts, right. So we now get Tx, the unknown period, in terms of 1 second if I make it Ts as 1 hertz, right, or I will get in terms of millisecond if I make Ts as 1 millisecond, or in terms of microseconds if I make Ts as 1 microsecond. Once again, the internal local oscillator frequency at that particular appropriate point is fed, and fed as one input to the AND gate that feeds the counter, right. Then it is possible to ratio mode. So ratio mode count is equal to Ta by Tb, where A and B are two inputs, unknown inputs, right. So and please always note that whatever the count displays, it displays the integer part of this division, right. If Ts by Tx happens to be 100.0172, the counter will simply display only 100 because the counter is an integer counter. So it can display only the integer part of whatever division I am putting, right. That should be understood, right. It is also possible to operate the counter in the elapsed time mode, where you can start the counter, stop the counter either manually or with respect to some waveform, right. Now applications of the counter, straight away of course I can measure the frequency of an unknown waveform, right. When we measure the frequency of the unknown waveform, we choose the period of measurement as 1 second, 1 millisecond or 1 microsecond to get hertz or kilohertz or megahertz. Now the other thing is I can measure the period, the time period of one cycle of my input in the time period mode, and in that case I get the period as seconds or milliseconds or microseconds, so many microseconds, right. Now if I look at the frequency mode, in the frequency mode, because I am measuring frequencies, when I measure low frequencies I will get smaller number of significant digits. For let us take an example, I am measuring 50 hertz, the power supply frequency. Now I put frequency mode and choose 1 second, I will get a count of 50, right, because in 1 second 50 hertz will give me 50 cycles. So the counter will count 1, 2, 3, 4, 5 and come to 50. And if I look at the resolution is only 2 digits, right. So it could be in error because of the plus or minus 1 count by 49 or 51. Now I take the same 50 hertz, I use time period mode and then I use 1 megahertz as my TS, right, Fs, then I will get 20,000 counts, because 50 hertz means 20 milliseconds is one period. In 20 milliseconds I will get 20,000 microseconds. So the counter will count 20,000. My resolution now is, the significant digit is 5 digits, right. So I will have either 19.999 millisecond or 20.001 millisecond, even if I have a plus or minus 1 count error, right. Moral of the story is that it is better to measure the time period when you are measuring low frequency, right. Similarly at high frequency, let me say I am going to measure 10 megahertz, right, 10 megahertz signal. Now I measure in the frequency mode, I put 1 second, how many counts I will get in 1 second? How many counts I will get? 1 megahertz I will get a million counts, and 10 megahertz I will get 10 million counts. So the count that I will see on the display will be this 10 megahertz, right. Of course it is hertz, finally it will be. So 1, 2, 3, 4, 5, 6, 7, 8 significant digits, right. Now I want to measure the time period, right. I choose 10 nanoseconds, because most of the timer counters will have the lowest resolution on your period mode would be 10 nanosecond. So I choose time period mode, I put 10 nanosecond, 100 megahertz as my clock, right. So what will be the count I will get? 10 megahertz is 100 nanoseconds. So if I put 100 megahertz I will get a count of 10, right. My significant digit again gone down to 2, right. So if you have low frequency, it makes sense that you use the time period mode and measure the time period, you get better resolution and large number of significant digits. If on the other hand high frequency, it is better to measure the frequency mode, where you will get much better resolution and higher number of significant digits than going into time period mode, right. So these are the two extremes. So at some point it would so happen that it is immaterial whether I use the time period mode or the frequency mode, I will get the same error, right. So if I have somewhere in between, I get the error, because this will be plus or minus 1, this is always plus or minus 1 hertz, this is plus or minus 10 nanoseconds, ten into plus or minus 1 into 10 nanoseconds, right. This is plus or minus 1, right. So somewhere in between, whether I get frequency or time period, I will get the same number, right, same number of significant digits. So plus or minus 1 really immaterial. Please think about it and try to find out at what frequency or time period I get that condition satisfied. Okay. Now, so we can measure frequency, we can measure period, we can also measure rate of two different frequencies. I want to find out f1 by f2, or I want to measure t1 by t2, it is the same, right. I can use the ratio mode and measure ta by tb or tb by ta, it depends upon where I feed the input, right. Then the elapsed time period mode, we already say that if I do it manually, I can make it as a start stop watch, I can find out how many seconds have elapsed or how many milliseconds have elapsed between the time that I gave a start signal and gave a stop signal. If the elapsed time period mode is chosen from the external or internal time signals, then it is possible to use them to measure certain things that are normally not measurable. For example, let me say I have two sine waves, I have one sine wave, then I have another sine wave, right. I want to measure the phase shift, right. Of course, we can choose a cathode ray oscilloscope, feed this into x and y, get the ellipse or circle whatever we are getting, and then from that we can calculate. Whereas we can use the timer counter, right. First I measure the time period of, I call this as signal A, FA, right, and then once I get the time period, then I choose the elapsed mode, right. In start with A signal, this is FA, and stop with AFB, and on my analog comparator at the input I choose 0 level and I choose direct coupling, there is no inversion, so which means slope is positive, right. So if I do that, the binary signal I will get out of the comparator would be something like this, right. This is 1, this is 0, right, and if my timer counter is rising edge sensitive, right, the counter will start here, so that is the start of the counter, and the counter will stop here. So if I do this, then the elapsed time phi will be measured as a count, right. So the actual phi I can calculate is the count I got in the elapsed mode divided by count I got for the TA mode, time period mode, into 360 if I want in degrees, or into 2 pi if I want in radians, because I know one period is 2 pi radians or 360 degrees, right. So using a timer counter we can measure the phase between two sinusoidal signals, right. And we can also measure, if these are already square waves or any other waveform, the time one waveform goes through a zero crossing to the time the other waveform goes through a zero crossing. It need not be exactly zero crossing, because I can always shift my comparator and find out where I can make a measurement, right. So I can also measure when the waveform attains a particular level, right. So I want to know how much time it takes for this waveform to attain a level of 1 volt, right. So in that case I can give FA as the start signal, choose my zero crossing at 0 volts, I give FB also the same signal, but choose the level for the comparator to be 1 volt, right. Then the comparator output will become 1 only when the input of FA attains 1 volt. So I will get a count which tells me how much time the signal FA has taken to go from 0 to 1 volt, right. That is also possible. Okay, for a very long time the timer counter was the only digital instrument that was available for use as an indicating instrument. People were trying to get a digital instrument for measurement of every other quantity that you can think of, basically voltage, current, resistance. We are all electrical engineers, we only look at those numbers, right. So in spite of the fact that the digital system itself was in vogue right from the 50s to 60s, right, the very first breakthrough came in measuring a voltage or current using the digital domain in the late 70s, right. Thanks to the development that took rapid development that took place in the integrated circuit technology, people could develop large number of transistors in one integrated circuit and make a complex circuit, right. So even though chronologically the digital voltmeter, as we know, right, the digital voltmeter came much later than other developments that we will learn a little later, right. I have juxtaposed the chronological sequence because the digital voltmeter has something common with the digital counter timer, right. So if you look at the digital voltmeter block diagram is simple. I have a display, digital display, right, because the 3.5 digit DVM is so popular and very cheap today, you can buy it for few hundred rupees, right. We will start with the 3.5, right. Unlike the timer counter, in the digital voltmeter 3.5 and 4.5 are the workhorse, are very popular all over the globe, and higher resolution 6.5, 8.5, even you can get 12.5 digital voltmeters, but they are very expensive. Okay. Let us see why. So we have the display, we have the counter, right. looks somewhat similar to our timer counter, right. Only thing is now I want to display something that is changing, right, not 1 or 0, right. So we must have some mechanism of converting whatever I want to measure into either a time period or a frequency, because the moment I put this counter and display I can measure frequency or time, right. In a conventional digital voltmeter what we have is whatever is the input voltage we convert into time and measure the time, okay. The principle we will see in a little while from now, how we convert, right, a given voltage into time. So a digital voltmeter is more or less a timer counter, right, but specially made to measure voltages, right. So if I really look at the overall internal circuit, we have a simple op amp integrator and a comparator, counter, we have digital logic and the comparator output goes to the digital logic. I call this as Vc, right. Okay. Now the input to the integrator R C goes through a switch. The switch is controlled by the digital logic. It is an SPDT, single pole double throw. So I have 1 2, I call this as switch S1. The one position of S1 is once again connected to another switch which is again a single pole double throw switch. I call this as S2. So this is S2, this is S1. Let me use a different color so that we do not misunderstand the box. One position of this switch is connected to plus VR, the another position is connected to minus VR, where plus VR is a DC voltage of magnitude VR and sign positive. Minus VR is another DC voltage of magnitude VR, but polarity negative, right. And if I look at this op amp, the moment I connected the non inverting input to ground, right, the inverting input will also be at ground potential if the op amp is working properly, right. We call this as virtual ground, right. So the operation is simple. We will start at time t equal to 0. Assume at time t equal to 0 the voltage across the capacitor is 0, right. Okay. So I have the voltage across the capacitor 0. Okay. We will see how we can get this condition a little later, and then I connect switch S1, the digital logic connect switch S1 to position 1. So we will also put the digital logic here, So, we have enter, we put S1 is in position 1 and S2 I do not care, wherever it is let it be there, because it is not connected into the circuit yet, right. And I am assuming that the input voltage is negative. It can be negative or positive, we will look at it a little later. To understand, it is better that we assume that the input voltage is negative, right. So, which means I am connecting a minus V in here, this is ground, voltage across R is minus V in, right. If I have a voltage V across R, there would be a current in resistance R, V by R. So, that current, because it is minus V in, the current will go in this direction. So, I will have minus V in, so current will go in this direction, this is V in by R, right, in this direction. Now, the op amp as an ideal op amp does not take or supply any current at the non inverting input. So, all the current has to come through the capacitor, right. So, the capacitor current will also be V in by R in that direction, right. So, when I supply a current through the capacitor, right, the capacitor would get charged, right, and the voltage of the capacitor Vc would be 1 by C integral I dt, right. I is nothing but V in by R dt, and I can remove R because R is a constant, and if V in is a constant, then I can say this is V in by C integral dt, or this is V in by RC into T, because integral dt is nothing but T, right. So, the as time progresses, if time is 1 millisecond, 2 milliseconds, 3 milliseconds, this voltage will rise, 1 millisecond into V in by RC, 2 milliseconds into V in by RC, 3 milliseconds by V in RC. So, if I look at the voltage across the capacitor, the voltage would start increasing at a particular slope V in by RC into T, right, that is the slope, V in by RC would be the slope. We do this for a certain amount of time, let us say T1, right. Now, what will happen to my comparator output? My comparator output, because the capacitor voltage is positive, the output of the op amp has to be positive, and the comparator will give me a 1, right. So, the comparator output at this point of time will raise 1 and continue to be 1, right. So, we now wait for T1 seconds, T1 is over, no, we continue to wait. If T1 is over, at the end of time period T1, we check Vc, now it is 1, right, okay. If it is 1, then connect switch S2, S1 to position 2, S2 to position 2, S2 to position 1, right. That is the logic, we see why this logic later, right. So, now what happens? At end of time period, this gets connected to 2, which means S1 comes into picture now, right. So, S1 is connected to position 1, which means plus VR is connected to the integrator, right. So, now this input is no longer negative, the input is positive, and the voltage is plus VR. So, the current would be VR by R, because the voltage across the resistor is VR, current is VR by R. The same current has to flow through the capacitor. So, the capacitor current is also VR by R, right. Now, the capacitor is having a current which is already charged in this direction. Remember, this is the Vc at end of Vc at time t1, right. Now, the current is in the opposite direction. So, the capacitor would now getting charged with this terminal as positive. That is only possible if already the charge in the capacitor is removed, right. Earlier the current was putting charge in this direction, now I am removing the charge from the other direction. So, the capacitor would start discharging and the slope would be VR by R, right. Now, we look at the comparator. At this point the comparator would change state, this is 0, this is 1, this is Vc, right. So, now we look at Vc once again, Vc, right, and is it 1? Yes, we continue to wait. When Vc becomes 0, we say out t2, the time period that I measure. So, this is t and this is time period t2, right. How do I check whether time period t1 has been achieved? How do I measure t2? With my timer counter, right, because that is what the timer counter can do, right. In the first place I use the timer counter, I set a count value corresponding to t1 and I start counting down or counting up, whichever way, right, and once the count value is reached or once 0 is reached, if I am counting down, I say okay, t1 is over, right, and then when I want to count, I reset the counter, give a clock to the counter and start counting the time in terms of milliseconds or microseconds or seconds, whatever I choose, right. So, I can set t1, measure t2 using a counter timer, right. Now, at the end of measurement, we make the measurement t2, we have now V in by Rc into t1. What is this? The total charge accumulated by capacitor in time period t1, right. That must be equal to Vr by Rc into t2, because in t2 time I have discharged all the charges in the capacitor, I have made the charge in the capacitor go to 0, right. So, now I can cancel Rc on both sides, then I will get T2 is equal to T1 by Vr into Vin. So, the measured value T2 will give me the count value T2 is proportional to Vin, right, and I can see that the proportional constant is T1 by Vr, right, the proportionality constant is T1 by Vr. So, if I make this T1 by Vr to be 1, then T2 will straight away measure Vin, right. How do we do? For example, I can make T1 is equal to 1000 counts, right, because I have chosen 3.5 digit, I assume that we go with 3000 counts. If it is 4.5 digit, I will make it as 10,000 counts, right. So, 3.5 digits, we make this T1 as 1000 times whatever time period, right, 1000 times Tc, Okay. Now I make VR is equal to 1000 millivolt, 1 volt, right. I call it as 1000 millivolt. Now if I use these two things, I will get T2 is equal to 1000 times Tc, and VR is 1000 millivolts into Vin. So now what I have done, I made it 1, of course Tc is there, T2 is also measured as Tc, right. T2, if I get some count, let us say I have D1, D2, D3, D4 is my T2, right, because I have 4 digits, it could be 1, 2, 3, 4, right, for example. So then T2 is into Tc, so now I can cancel Tc, Tc, so my D1, D2, D3, D4 will show me Vn, right, and in what units? Millivolts, right. So now I have whatever count I get, if I am getting a count value of 1, 2, 3, 4, and I know it is 1234 millivolts, right. So provided I keep T1 as 1000 and VR as 1000 millivolt, right. So we get a reading like this, and what is the maximum count I can get in this particular 199, because it is 3.5 digit, I get 1999 millivolts, or I simply say this is a 2000 millivolt full scale digital voltmeter, right, 2000 millivolts full scale digital voltmeter. 2000 millivolts is nothing but 2 volts, right. So instead of saying this as millivolts, I can put a point here, I say it is 1.234 volts or 1999 volts is the maximum that I can measure. We call this as 2 volts full scale, right. So the T2 will now give me, please remember this is irrespective of the clock frequency I choose, right. We will decide on clock frequency a little later. So I can choose a clock frequency of 1 kilohertz, 1 megahertz, it does not matter, right. I will still get the values provided the op amp does not saturate, all those things will come into picture, which will force us to choose a particular clock frequency, right. And so if for example my Vin is positive, right, if Vin is positive, what is going to happen? If Vin is positive, at the start itself here S1 is equal to 1, T1, right, what will happen to, so this is going to be Vin by R, I think this color is not good, so let me choose the red color, right. This is Vin by R is the current, now the current will be in this direction, right, and the capacitor will be charged this terminal as positive and this terminal as negative, right. So this is now the current, capacitor charging current will be in this direction, Vin by R. So how will Vc look like? Vc would now go in the negative direction, right. Vc is no longer positive, op amp output is going to be minus, right. At the end we check Vc, the comparator voltage, so I have put 2 Vc's, voltage across the capacitor is Vc, I will call this as Vcom, comparator voltage, right. The comparator voltage, because the voltage is negative here, what will be the comparator output? 0, right. So for the Second case, when V in is positive, the comparator output will be 0 at the end of T1, right. So, we look at the comparator output will be 0, then we change the logic, S1 is equal to 2, S2 is equal to 2, right. So, S1 is equal to 2, S2 is equal to 2. Now, what happens? Minus VR is connected here, right, minus VR is connected here. So, the terminal will become minus here, plus here, the current would go in this direction, the current would change the direction, this would be VR by R, right. Once again the capacitor will be discharged, the negative charge stored in the capacitor, right, the negative voltage stored in the capacitor would be discharged, right. Let us say it leaves with another T2, T2 dash, because minus V in can be some other value, right. We do the same thing, we check Vc, if it is 0 we continue waiting, if it is 1 output T2, right. When it becomes 1 here, the count, right, at exactly this point the comparator voltage Vcom would rise to 1 level, right. So, once again I measure T2, rest of the circuits are, rest of the equations are same. At the end of T2, whether I go positive or negative, V in by RC T1 must be equal to VR by RC into T2. It is immaterial whether I choose input to be positive or negative, right. Now, I can also look at the comparator. If the comparator is 1 at the end of time period T1, I know polarity of V in must be negative, right. At T1, right, at T1, if Vcom is equal to 1, V in is negative, I know. At Tcom, at T1 Vcom is equal to 0, I know V in is positive. So, I not only measure the voltage, but I can also measure the polarity of the voltage, right. By simply choosing a logic, I can measure the polarity of the voltage. So, a digital voltmeter, which is basically a timer counter with additional logic, right, that logic has to implement this flow chart, would measure both positive and negative voltages. Because there are two slopes, right, of the integrator in a digital voltmeter, it is also known as dual slope voltmeter or dual slope analog to digital converter. Because my input voltage is analog, output is digital, I call this as a dual slope analog to digital converter. Analog to digital converter, we popularly call it as ADC. Today, if you measure, if you buy a digital instrument, you can be 100% sure that the voltmeter, right, the device is made of a digital voltmeter, and that digital voltmeter is based on the dual slope principle. Okay. It does not mean that there are not other analog to digital converters, there are other analog to digital converters, we will learn about them, but for human interface this is the best. Right. I will stop here, we will see in the next class.